Hi there. Welcome back to the formulaic approach. Now, today we are going to be talking about current density, drift velocity, electric field, resistivity, and conductivity relationship. So, what I plan to do in this video is to relate all of these concepts together, both mathematically and contextually, so that you can understand what they really mean. Then I plan to also show you, as a way of proving of the relationship, the microscopic electric current in the microscopic scale. Okay, I will also be proving the Ohm's law, the microscopic representation of Ohm's law. I'm just going to use mathematical equation to link all of these things together so that they all make sense at the end of the day. Now, so stick with me from the beginning to the end in order to understand. So you're also going to understand the use as well. Now, we are going to begin with current density. So what is current density? Current density is actually just the number of, or the amount of current per unit cross-section of a conductor. So if I have a conductor that looks like this, for example, here's my conductor, the cross-section is circular, right? The cross-section is circular. Now, the current density, not charge density, the current density of this conductor is basically the amount of current that is flowing per unit of the cross-section. Okay, so per unit of this cross-section, that is each of these cross-section, if I could isolate it into the smallest cross-section of this thing, the number of current of electricity flowing is going to be the current density of this guy. Now, it is denoted by J, and we said it's the current flowing per unit cross-sectional area. All right. Now, know that current density J is a vector quantity because it has magnitude and direction. But current itself is actually a scalar quantity. Now, I've explained to you that it's also a tensor quantity. The reason why we call it tensor quantity is that it has the attribute of both vector and scalar in a way, because it has direction, it flows from positive to negative. But why is it not a vector quantity? And it has magnitude already, Why is it not a vector quantity? The reason is because the current flowing through a metallic conductor, the addition of current follows the scalar arithmetic, just simple arithmetic operation. All right, so that it is unaffected by direction or the mode of arrangement of the system. Okay, so if there is a conductor that's like this, another conductor like this, another conductor like this, and I say a current of 2 amperes, flows in this direction, and a current of 4 amperes flows in this direction, and they all come out, the entire current now come out here using Kirchhoff's rule, of course. Kirchhoff's rule or Kirchhoff's rule tells us that the total current that enters this junction leaves, right? So at the end of the day, it proves that the total current that we're going to find here is going to be 6 amperes, which proves that what we basically did was just to add 2 and 4 together scalarly. And so it has the attribute of both vector and scalar quantity. But if you do see in your option scalar, you should choose scalar, because this is a more practical sense of vector and scalars. Do you understand? This one, since it follows scalar addition, we call it scalars. Is that clear? All right, but the point is another thing. I'm going to show you another mathematical proof of its nature, the nature of current being a scalar quantity. From here, I'm going to show you. So I said that current density is current per unit area, which means, of course, that the unit of measurement is going to be amperes per meter squared, or amperes per meter squared, this way. This is the unit of measurement of current density. Keep in mind, J, the J vector is the current density, current is I, A is area. But this area is an area vector, not just cross-section, okay? It's an area vector because it is affected by direction. That is, it is directional, okay? And the orientation changes the orientation will affect our product, the orientation of this cross-section. What that means is this: if I were able to isolate a cross-section of this wire, so I have a cross-section that looks like this. Now, if my cross-section looks like this, okay, the amount of charge, the current flowing through this cross section is going to be flowing through, let's just say a plane. Let's give it a plane. So I use one line for a plane. So all of my current flowing will flow in this direction, in this direction, in this direction, in this direction, in this direction. You see how much they can cover, okay? See, they are able to, there's a lot of current flowing from here to this point. But if I were to, you see this orientation of the guy, I pointed this side, I tilt it a little, I tilt it a little bit. What will happen is that the amount of current that will now flow will change. Because if I tilt this thing like this, it's going to have this orientation and look something like this. What happens, what that means is that the amount of current that is going to be touching it will just be the current from here, current in this direction, current in this direction, current in this direction. The rest will pass without touching it, or will pass without going through it. Do you understand? So that shows you that this area here, the cross section of this guy is an area vector. Do you understand? So, and as an area vector like that, the area that it will touch is going to be the angle, here angle cos theta. I made this angle with the original vertical, okay? So the value of the area that is touching is going to be a cos theta, okay? The value of the area that it will be touching is going to be a cos theta. All right, I now said that, now I said that the J vector, the current density is the current density is a vector quantity. I said that current density is a vector quantity. Now, if you want to also see my other proofs on this, I'm going to link the video of electric flux. I'll link it in the description. I don't want to get into what this is, okay? I don't want to use this to prove something to you. Now, if you have seen my video on vector, I told you that there is scalar product, there is dot product, okay, and there is dot product and cross product. So if you look at this guy, current from here is going to give us J times A, which is J vector dot A vector here. So, and is A vector in this place cos theta, okay, where if theta is 90 degrees, then it means that it is 1. That's maximum. So maximum current flows through a conductor or a cross-sectional area at the maximum current will flow through the cross-section. Maximum current will flow through the cross-section. The maximum current will flow through the cross-section at theta equals 90 degrees. When is theta equals 90 degrees? So what I'm talking about is, look at this guy now. Look at this. Now look at, let's say this is the cross section of the wire. So now the amount of current that will be flowing through here is going to be much. Unlike if I tilt this thing like this. Once I tilt it, some current will pass through, like I said here, without touching it. But another thing you should see is this, that if I slant this guy like this, no current at all will be touching it, given that it's a cross section, okay? No current will be touching it at all. So the current will be 0. That is, if the area is at 0 degrees or 180 degrees to the direction of the current, is that clear? To the direction of flow of current. If the area vector is 0 degrees with the current flowing, then it means that there will be no current flowing. Do you understand? So no current will be touching that cross section. That's just what it means. Exactly. There will be no current flowing when the area vector is 0 degrees. How did I know it's 0 degrees? So think of it as a very slim paper now. Look at it as a very slim paper. When it was staying this way, think of my markers as the number of currents that are flowing. The number of markers that will hit this is very much compared to this. Maybe only one marker will hit this. But of course, because our cross section is thinner than this, almost no current will pass through it. Do you understand? So minimum current at theta equals to 0 degrees. Minimum current is seen at theta equals to what? 0 degrees. All right, so that said, current density is a vector, and current is scalar, and this proves it. This is also dot product, and dot product is scalar product. Do you understand? Dot product is scalar product. Vector A times vector J cos theta. So that also shows why it is a scalar. Now, let's continue to drift velocity. So I'm going to just leave this equation somewhere here, that J equal to I over A. All right. Now, still using the same cross section, let's talk about current. Now, why do we need to talk about current density? I'm sorry, I didn't mention that. This is the reason. Because it is with current density that we're able to understand that the size of the conductor actually has a lot to do with the quantity of current that will flow in it. What that means from the equation is that the wider the wire, the lower the current density. And the wider the wire, yes, the wider the wire, the lower the current density. Yes, and I'm coming, let me quickly. But the higher the current flowing, yes, the higher the current flowing, but lower the current density. Do you understand? And that's just look at the equation. It's just the equation you use. Look at it. The vector current density is inverse proportional to the area. Okay, so what that means is that the wider the cross section of the this thing, the higher the current, okay, but lower the current density. Do you understand? Now, I now said that. So that's why we need it. So physicists define current density as the quantity of current flowing per cross-sectional area. All right. Now let's talk about the drift velocity. Now drift velocity is basically the velocity of each of the charges that are moving. So that is current in the microscopic scale now. Microscopic view of current. Current microscopically. We are going to bring or bind all these equations together very soon. So current microscopically is just, we are looking at the same conductor, okay? We are looking at the same conductor, and the cross section is still A. Now, charges flow in like packets of volume, exactly. And what that means is that the volume, volume of the smallest volume of this conductor, the smallest volume of amount of charge carried here is going to be dV. Do you understand that? That's the volume of charges that are swept as the current is moving. Okay, I didn't mention this before. Why does current move? Current moves because there is a difference in potential between the two ends of the conductor, and that is why it moves to a point. Current electrons are just trying to move to a point of lower potential. They move from higher potential to lower potential. So now after that, as they are being swept in volume. So the smallest volume there is dV, and it's going to be dV is going to be, volume is area times height, right? In this case, or area times distance. In this case, it's going to be that cross-sectional area times the small distance moved, which is dx. Is that clear? The small distance moved by the electrons, dx. And we already know also that velocity is going to be equal to, now the velocity, which is drift velocity in this case, is now going to be equal to the distance moved per unit of time. So the small distance covered over small time interval. So by the time we do this, it means that dx will be equal to v sub d dt. Take note that this v sub d is not v sub d is drift velocity. So from here we can therefore say that the big V is equal to A times dx, which is v sub d dt. Do you understand? But also keep in mind also, since we are looking at the packet of volume swept, so it means that the total charge here, the total charge per volume, the total charge or the average charge per volume is going to be equal to number of free electrons that are flowing. Let me repeat that. The total charge per volume in each of those small packets of the volume of charge swept. So that's total the charge of each volume, charge per volume, is going to be number of free electrons in that volume. Does that make sense? So which makes it be that the charge is going to be the total volume dV times the number of electrons times dV. So from here we can say that since dV is this, then we know that dq will be equal to ne dV. So that is ne dV, and dV is this. So we say that ne dot av sub d dt. Then dq therefore becomes ne av sub d dt. Okay, still the same thing. All right, now, and we are looking at current in the microscopic scale, and the current is actually average current is total charge per flowing per time. Okay, so and this is average current. Okay, average charge, total charge per time, dq dt. All right, remember steady current is just I equal to q over t, where the flow is steady. So but when we look at current, we actually just take current as the average charge, okay, per average time, flowing per time, and that becomes dq over dt, wherein we can therefore say that I will be dq, which is now ne av sub d dt over dt. So dt takes care of dt, and I becomes ne av sub d, where v, small v sub d is drift velocity. Is that clear? That is drift velocity. So now, looking at current density in the microscopic scale, we are already mentioning them. You know that current density, recall this equation 1. Let's call this our equation 2. So in equation 1, we have that current per unit of area. So it means that microscopically, joules, current density is actually ne av sub d over a. Does that make sense? So area will cancel area, and then we know therefore that J current density is going to be equal to ne v sub d. Do you understand? Let's be sure we didn't miss anything out. Okay, ne v sub d, and that is current density. Then the relation between current density and drift velocity is just this, that current density is direct proportional to the drift velocity, while drift velocity is going to be current density per number of charge flowing per volume. Just drift velocity will be the current density divided by the number of charge flowing per unit volume, number of charge carriers flowing per unit volume. So that's that. So let's call this equation 3. Now I'm going to put it here. So we have looked at current in the microscopic scale. Let's now look at the electric field. Let's look at the electric field. Now remember that we have this equation now, that J equal to N EV sub D. Okay, let's call this equation 2. Now from here, you remember that electric field is just equal to E equal to F force per unit charge. Do you remember? So in this case, it's going to be force per unit of charge carrier by using the elementary charge E. Is that clear? Alright, if that's the case, and remember that force is equal to mass times acceleration. So it means that if the charges are drifting, then they have an acceleration. There's a time when they are being accelerated, even though they are not accelerated continuously. I've explained that before in my video where I proved this. So do well to see that video. I'll link in the description. They are not accelerated continuously because they are hitting the lattices of the wire. They are hitting the cable, the metal lattice of the cable. They are hitting it, and it's those hits, those collision with those lattices that is causing vibrational that is causing them to vibrate, and that vibration is generating heat energy. Do you understand now? So, and it's that heat energy that is felt as the the energy that is being lost as heat, as internal resistance of that cable. Do you understand now? All right. So, like I said, they don't accelerate forever. So, the acceleration is going to be the drift velocity per unit of time in between collision with the lattice of the metal. So that is in between the metal, the time in between their collision, the first collision and the second collision that happens is going to be this time here. Okay, we represent with the tau, and then v sub d therefore becomes a tau. Does that make sense? And recall that F is equal to ma. What that means is that since A equal to this, right? Since A is equal to this, then F will be equal to mv sub d over tau. Now what that means is we are going to use this to represent this in the equation, to replace that in the equation. And our E vector, electric field becomes mv sub d over E tau. Is this clear? All right. So from here, drift velocity can also be written as E tau over m times E times electric field. I intentionally separated this electric field, okay? There's a reason why I separated it, and I'll show you soon. Now, also remember that electric field is equal to the voltage per distance, right? Voltage over R, or voltage over distance, okay? So from here, now voltage, the R which will be the distance here, is going to be the length of the wire. So I'm going to change this equation to E equal to V over L, because the electric field is just the electric field I set up between the two ends of the wire. So it means that the electric field is just going to have the length of the wire. It's just going to be from the beginning to the end of the wire. So if this is the case, then we therefore know that we already have this, okay? So we can therefore say that now we can use this equation. Let's call it equation 3. We can substitute it into this equation first. All right, I'm already linking the current density and electric field, because this is what's going to give us that current density is going to be ne v sub d. Then J therefore becomes ne v sub d is now E tau dot E tau over m dot E multiplied by electric field intensity, so that J becomes ne squared tau over m dot E. Do you understand now? Now this is the relationship between electric field intensity and current density. This is the relationship between what? Electric field intensity and current density. Now, this leads us to Ohm's law microscopically. So the microscopic relationship, the microscopic representation, microscopic form of Ohm's law is actually here. Since J, recall we said is ne squared tau over m dot E. All these values will be intrinsic to the wire, and that property of the wire, this will be called conductivity of the wire, because all these values, all these will be intrinsic to the wire. They will be dependent on the wire. Remember, the electric field will not be dependent on the wire. It is these ones that will be dependent on the wire. Conductivity, which is denoted by sigma, and that gives us that our J is going to be this E, sigma E. Do you understand now? So this is the microscopic form of Ohm's law. Okay, this is the microscopic form of Ohm's law. That is the current density. Now, what does this tell us? This tells us that the amount of charge, that the current density is dependent on the electric field. Okay, and also that the electric field, that the current density is also dependent on the conductivity of the wire. So a more conductive wire may have a higher current density, and a lower conductive wire may have a low current density. All right. So we have you have another equation here that says that J equal to conductivity times electric field. So I'm going to clean all of this now. Okay, then I've not worked with this. Let's see what we can do with that. Actually, from here, I'm thinking we can already generate an expression for both, since we have found out what conductivity is. Conductivity simply means how much permeable to conducting of electric current a particular conductor is. How much an electric conductor allows electrons to move through it. Do you understand? That is just conductivity. And remember that conductivity is inverse of resistivity, because resistivity is how much hindrance a particular oh, I'm sorry, this is the conductivity. Oh God, this is the resistivity. That factor there is the resistivity. No, N is squared E. Is that resistivity or conductivity? I think this is conductivity. Okay, I think it is conductivity. I'm thinking it's conductivity. All right, let's try and use it to prove Ohm's law, to generate an expression for resistance. If it works, then it means that it's conductivity. Can't really remember that much. So since conductivity is inverse of resistivity, then we know that J therefore will be equal to E over this, E over resistivity. We know that resistivity is how much hindrance a conductor poses to the flow of electric charges. All right. So if this is the case, then we know that. So let's call this equation 4. Okay. So having all of this equation, we already know that J is I over A. We know that the same J is conductivity times E. And we know again that the same J is E over rho, and E is V over L. Okay, from here, let's see what we can derive. Let's see if we can derive something. And also that V is equal to IR. Okay, such that I will be equal to V over R. Let's write it in terms of current. I'm writing in terms of current, since we are dealing with current and all here. Okay, so from here, looking at all these equations, I can say that I want to generate this expression for resistance. Let's see if we can generate an expression for resistance using this. Which one should we use? Let's use this, since this one has resistivity already. So J, which is I over A is equal to E, which is V over L times rho. Okay? Now if this is the case, remember that current is also V over R. So what that means is that we have here V over R A is equal to V over rho L. So V takes care of V, and we have that we have, by the time we cross multiply, RA is equal to rho L. Then it means that resistance, if you divide both sides by A, yes, we are correct. If you divide both sides by A, R will be equal to rho L over A. So this is the derivation for resistance, rho L over A. What does this tell us? This tells us that the longer the length of the wire, or the longer the conductor, the higher the resistance it poses to electric current. And the lower the length, the higher the lower the resistance. But the higher the area, the lower the resistance, and the lower the area, the higher the resistance. Is that clear? So this is what brings them together. This equation, this equation, and this equation are very fundamental, and you should take note of them. So take note of all the equations I wrote down, as well as these two. They're very important. So that'll be it for this video. I hope I've been able to tie them up mathematically. Conductivity, resistivity, okay? So what that means is if I wanted to write it in terms of conductivity, then I'll have that, So I've proven to you that value, that n is squared E over m is actually conductivity. So if I wanted to write this expression in terms of this, then what we'll have is, since rho is inverse of conductivity, then we are saying that R will be equal to L over sigma E. Okay? So from here, we therefore know that that sigma, okay, we didn't even write an expression for resistivity. Resistivity here, therefore, will become RA over L. Okay? Meaning that, okay, this is an expression for resistivity. Okay? Meaning that the higher the area and the higher the resistance, the higher the area times the resistance, the cross section times the resistance of the wire, the higher the resistivity. Okay? But here, and the longer the wire, the lower the resistivity. But here we have that we have sigma equal to L over RA. You see, this proves that they are inverse of each other. If you make sigma sorry forward. So that'll be it for this video. Do also subscribe to the channel. In the next video, what I'll be doing is I'll now be showing to you current, instantaneous current, and instantaneous current and average current, and how to solve questions on them. God bless you as you subscribe. Please share the video with your friends as well.